Okay, the record is on. I have previously mentioned about the indeterminate structure. Oh, that's not that's the wrong subject. Here it is. Okay. I have previously mentioned about the indeterminate structure before. Okay. And let's say you can view the structures this that let's say I have a cantilever beam. Okay. And then this kind of situation will give the displacement at the end of your structure. So if I call this A and B, so let's say a typical structure will have delta B. Okay, your structure will come down like this. We can view the situation as this. Question is it possible for you to try to find the load P that will bring this delta B to 0? Okay, so that of course we can. We call this delta BB. If delta BB is equal to this capital delta B, we set that equal to each other. We can therefore calculate the load P that will cause the same displacement but in the opposite direction. And with this reason, I can rewrite the situation as this. We have a structure with a roller, because with a situation like this, the roller has the reaction, correct? So the reaction of the roller is pretty equivalent to this load P. So you can view this situation, which may look like a complicated structure here, as a typical structure like this with the load to try to help it to secure the zero displacement at the roller. Okay, and this, because sometimes it is easier to look at the situation like this, but when the structure gets more complicated, it may not be this easy. So this is your indeterminate structure, okay? Because you have 4 reactions, but you only have 3 equilibrium equations. So with this, it leads to 1 equation short. So we call this a degree of redundancy. So this structure has 1 degree of redundancy. And as a result, you need to find extra equation to eliminate this extra unknown. Okay? And from this, we can split our indeterminate structure here into 2 conditions. The first is, of course, we must turn this indeterminate structure into a determinate one. But the catch is that turn it into determinate. But the catch is that it must be stable. You cannot create the determinate structure out of this indeterminate and make it unstable. Now we don't call this determinate structure because it is, something that is a result of the fact that we remove the redundant from our indeterminate. So this one is called a primary structure. A primary structure is a determinate structure whereby you can analyze the structure with your statics. And the fact that we remove the unknown until we have the primary structure will enable you to calculate this delta B. Okay? But then knowing this delta B is in fact 0 because you actually have the support here. So the real structure has 0 delta B. So in turn, you know that whatever your reaction here P is, it must be capable of producing the same amount of displacement, but in the opposite direction. Okay, so from this primary structure, I can achieve my extra equation, which we call the compatibility equation. Okay, and this goes like, because they are equal but in the opposite direction, so I can say delta B plus delta BB must be 0. So keep in mind that this delta B is the displacement of your primary structure. Oh, sorry. Primary structure. And therefore it's due to actual load, whereby this one is displacement caused by the reaction. Okay. So, and one common mistake that some students make is that they mix the two loads together. The first one is a primary structure. That one contains the actual load. But when you monitor or when you look at your reaction, the displacement caused by reaction is the displacement caused by the reaction alone. So in the second case that you look at, this one, the deflection caused by your reaction alone, it doesn't have the load. It's just the deflection caused by reaction. Okay, so I can just add more. That's just no other load. Okay, and sometimes let me add this up, because sometimes we don't know how much the reaction is. So anyway, before I say that, let me ask you this: is there any question? Is there any question? Let me give you a minute or two break. I'll come back shortly. Okay. It just I'll give you time to try to synchronize with this idea, and then I'll come back in 30 seconds. Okay. All right, I'm back. Is there any question regarding this? Okay. Anyone wish to speak? Okay. So let us go back here. Another way to handle this is that, because you can see that you actually do not know what P is. Okay. So I am going to rewrite this displacement thing. Plenty will follow, seems. Whoa. You know what? And I cannot stop it now. Silly me. Anyone know how to stop this lasso thing?
Stop what?
No, it takes forever. You can see that now, right? I want to just copy that silly beam, and now it takes forever. Can I do something about it? Okay.
I think it's done.
No, that's done. Thanks. So let my apologies on the hiccup. So let's say we focus on the reaction, just the reaction, okay? Now you know that whatever this is, the reaction has to produce the same amount of displacement as the external load, okay? So we call this delta BB. Notice that I use the lowercase b and two of them because if that is more than one degree redundancy, we need to have this because it gets more complicated, okay? Anyway, since you don't know what this reaction is, sometimes we just use a unit load, okay? And if this unit load, because it will be much more convenient for many people to just look at this as a unit load. So when I look at this, and I can easily calculate the displacement due to the load that is equal to 1, right? So I can say alternatively, use load equal to 1 to calculate displacement. And so delta BB is therefore displacement due to unit load, right? So what does that mean? Because you guys are living in the elastic world. So if the displacement caused by the load equal to 1 is equal to delta BB, what do I use? P, right? Doesn't matter what it is. The displacement caused by the load P will be proportionate with the displacement caused by the load equal to 1. And so this will become delta BB multiplied by P. Because it is elastic, so everything is proportionate. If you have the displacement caused by the load equal to 1, equal to delta BB, therefore the displacement caused by the load equal to P is equal to delta BB multiplied by P, right? And in this case, your compatibility equation will be delta B plus delta BB multiplied by P equal to 0. Right? So you can either do it like this, but this delta BB of yours will be in the form of P anyway. So incidentally, they are the same. Okay, incidentally, they are the same. But in the first approach, you just look at it as a displacement caused by P, and P you don't know. So this delta BB in the first equation will be in terms of P. But the second, you use the load equal to 1, and then you use the proportion to come up with the displacement due to P. So it will come in terms like this right away. they are the same, and you can easily achieve P now as minus delta B over delta BB, that kind of stuff. Okay, so first we can use displacement to calculate the extra unknown, because we can use that to set up our compatibility equation. Second, because this is the most important thing, so you guys listen carefully, because displacement depends on EI of your structure, correct? When you calculate your displacement, it always comes in terms of something EI. So that means for indeterminate structure, your reactions will depend on the properties of your material and your section. When you analyze your simple structure, a simple beam, a cantilever beam, you can go ahead and calculate reactions and so and so. But the fact that we use deflection to calculate the indeterminate structure means that if I change the E, or if I change the section so that the I also changes, reactions will change. For the first time in your life, the reactions of your structure depend on the property of your structure. Okay, so is there any question? So we are repeating this twice. I have done this in the past 5 years or so, introduce you to the indeterminate structure and then made a detour to calculate to the calculation of the displacement, so that you know why we need to do that. And we'll come back here to the calculation of the indeterminate structure itself, hoping that you get a better picture out of it. So is there any question? Okay, quiet as usual. All right, let's say that there is nothing more for me to say except we go to the example. Okay, so let us go back to this. Remember, we did this in the very first hour after the midterm exam. So the less we mention about the midterm, the better, right? So let's say we used to do this. I used to give you the calculation of the displacement of this. See, so we now know that if we have the external load like this, okay, the calculation of the displacement shows that the delta max here is WL to the power of 4 over 8 EI. So if I look at this again, the same beam, but this time I have the roller here. So right away, if this is your structure, this becomes the indeterminate structure, correct?
Yes.
Thank you. So this is the indeterminate structure. And your first job is to determine how many degrees of redundancy your structure have, because that will tell you how many compatibility equations you are going to need. But because I don't think anybody used this method to calculate the structure anymore, so I don't think there is any point to give you a hard life by giving you the problem with more than 1 degree of redundancy. So this is 1 degree of redundancy. So we need to turn this. Actually, I have the step somewhere that you may follow. Okay. This is useful, but it's pretty straightforward. Determine the degree of redundancy first, and then remove the unknown force to obtain the primary structure. So that is the step number 2. Okay. So we go back here, and if this is your structure, I deliberately paint the roller in red so that you can compare with what we have for the calculation of the displacement before. So the first step is now done. Determine the degree of redundancy. The second step is to create the primary structure. This becomes this. Okay. Remember that this is the actual structure. We remove one reaction to obtain our primary structure and enable us to analyze the structure. So I remove RB. Okay. And when I remove RB, as a result, we now have displacement. Okay. There. And to show you that there are so many ways to do things, and I'm not going to restrict you to write this or write that. So I'm just going to call this delta B now, small delta. Okay. And from previous calculation, delta B is equal to WL to the power 4 over 8 EI. Okay. So now the second step is done. Okay. If it's not done, it is your job to calculate this. So and that's one displacement. Now the next step would be to, we already did the unrestrained deformation of primary structure. We did that. Okay. Calculate the deformation due to redundance by applying the unit force, or you can look at the reaction itself. Here it is. Okay. So this is in fact step number 3. Step number 4, I am going to calculate the deflection of, you can say it's a primary structure. Yes, of course. Otherwise you cannot do it, of this. So now you have a choice to call this RB or to call this 1, but I prefer 1. Okay. So now in fact, we also have the formula to do this, right? But, you know, just to show you something, 1 becomes my actual load. Okay. So let's say this is alternative number 1. 1 is my actual load. If I am going to use the virtual work method, I have to apply the unit load, right? So yeah, so in this case, 1 becomes both your actual and virtual load. Right? Now 1 becomes both your actual load and virtual load. Now let's say I would like to make life a little more easier, because I prefer to look at the load as a downward displacement. So I am going to use this unit load. So let's say if I am going to use the virtual work, the moment, let's say I'm going to integrate from the tip because it's easier. So the big M due to actual load is X. And the small m due to the virtual load is also X. Okay? So that means my integral here, delta BB due to the unit load will be equal to integral from 0 to L x and x dx over EI. This gives me x cubed over EI from 0 to L. So it becomes L cubed over EI. But remember, this is the displacement due to the unit load. And so number 5, I think if we have this now, where is here? Okay, number 5, we assemble the deformation. That is the compatibility equation. Okay, so sorry, yeah, okay. So number 5, oops, compatibility. Now I have WL to the power 4 over 8 EI plus, remember this displacement is due to the load equal to 1, but I want the displacement due to the reaction. So this becomes L cubed over, oops, I forgot the 3, right? Yeah, it has to be 3. 3 EI multiplied by RB equal to 0. In this case, EI will cancel each other. And so RB turns out to be, it's gone, minus 3WL over 8. Why is it minus? This is negative because the reaction is in the direction opposite to my unit load. And you can see it is not equal because this takes 3/8. So that means on this side, the reaction must be 5/8. Okay, so that's one way to write it. Let me show you another way. Yeah, so we repeat the step number 4. Okay, instead of looking at that, now I have the reaction RB instead. Okay, so to calculate this, I apply the unit load. So now we have to be mindful of the sign, right? In fact, because this is, if you think this is, let's come back here, and if you think this is negative moment, you may write it down as minus x and minus x, but in the end it's the same because, you know, the load are the same. But in this case, the second case, you have to be mindful of your direction now. And the big M is now RBX, but the small m is now minus x, right? And RB is a constant. So in this case, our integral from 0 to L will be RBX minus x and then dx over EI. And fast forward a little bit, you will have delta BB equal to minus RB, then L cubed over 3EI. Okay, but in step number 5, we now have WL to the power 4 over 8 EI minus RB L cubed over 3 EI equal to 0. In the end, RB is 3 WL over 8. Okay, this turns out to be positive in the end because now we are using the upward RB here. Okay. So is there any question? Is there any question? So is there any question? 1 second. Is there any question? Hello, are you with me?
Yes.
Yeah, so please don't be afraid to ask questions.
Okay.
Be afraid of your grammar. Just if you have questions, just try to communicate with me. Worry about the grammar later, okay? If you have any, of course, I believe you must have.
Why at the fourth step of
Okay,
at the fourth step,
here or the
first one?
this okay.
Why the capital M can be X? I mean, why 1 can be the actual work?
Because we look at this. This is the second approach because where is my lecture here? Because we don't know what the reaction is going to be, right? So we can say because we don't know how much, we might as well start the calculation from a unit load. We don't know how much the reaction is going to be, so we don't really know how much the displacement is going to be. That's the catch. But let's say if we know the load is equal to 1, we can calculate the displacement of the load that is equal to 1, right? We can achieve that. But because of the fact that we are in the world of elastic, the load equal to 1, when you have the displacement of the load equal to 1, you can calculate the displacement of the load equal to 5 or 10, for example. If your load changes from 1 ton to 5 tons, the displacement is going to be 5 times greater than the displacement produced by the load equal to 1, right?
Yes.
So because we don't know how much the load is, we can say it's P or it's RB. So the displacement caused by RB will be RB multiplied by the load. The displacement caused by the load equal to 1. Right?
Yes.
We don't know how much that is, but we know it's going to be RB times greater than 1. So if RB turns out to be 5, the displacement is going to be 5 multiplied by the number that you get from the load equal to 1. That's the approach. That's one approach. Pick what you like. So let's say because we don't know how much it is, so we start from saying, okay, we're going to calculate the displacement of the load equal to 1. Because we now want the displacement of the load equal to 1. So 1 becomes your actual load. I can, because I try to leave the space on the right for that one, but I don't mind now. I'm going to write here. Okay. This is your actual load now. That's why, let's remove this. So 1 becomes the actual load. Now, if I am going to use the moment area method, we are not going to have the issue of this at all, right? I can easily use the moment area method to calculate the displacement due to the actual load, which is 1 in this case. But because I want to show you very earlier, because in the frame we are going to have to do this anyway, we choose the virtual work. So the load also becomes, the unit load also becomes your virtual load. If it may help you to reduce confusion, you can also write your virtual load separately and use your star, right? So this may become X and then 1 star. That help? But then this, you have this as the actual, okay? 1X, but 1 here is the actual, but 1 star X here because this is the virtual. But in the end, you know, 1 or 1 star, it just doesn't matter to me. So this may help you in the end. So you have 1 star stuck up somewhere in there as well. Oops, here we go again, you know, the sharing is gone. Tuesday morning, all the time. No problem any other day. Yesterday, no problem. Thursday, no problem. Okay, we're back in business. Okay, so is there any more question? Would you like me to go over here again? I don't want to go over too quickly. I believe that you guys are not very forthcoming with me. You reluctant. You relent because you are afraid to speak English. So that doesn't help your learning process. Okay, so let's not be afraid of that. Before I could use English like this, you know, I had days like yours before too, you know, and I had worse because whenever I made mistakes in my family, they mocked me to the degree that you know, sometimes you think you rather die. But I never mock students for using you know, bad English. So if you have anything in your mind now, if you want me to go over anything again, please tell me. So I will have to assume that you guys are okay. We cannot afford to stay silent until like 12:30, right? Hello. Very well then. So let's say I am going to have to move this. Okay, so let's look at another case. Again, we have done the calculation of the displacement of this before, right? In previous examples. So let us go back there and watch. More. Here, okay? We used to calculate the displacement for the mid-span deflection of this beam, right? Okay, but that one has a length L. So we now know that the displacement is this one. 5W L to the power 4 over 384 EI. So I am going to use the same knowledge here. Say if we have this situation, here. Now we have this pretty delay. Now we have this as our extra equation. So if this is the structure that you are given in the beginning, okay, if you plan to remove the reaction in the middle, you will have the chance to calculate the displacement right there. Okay, so that's how I could use the information that I have before. It's not that you have to remove that all the time. We'll come back to that later. But in this case, say the step number 1, you now also can determine that this is the structure with 1 degree of redundancy. And your choice to the primary structure will be to remove the reaction in the middle. So now you're going to have the structure that looks like this. Okay. We say A, B, and C. This is B. Okay. So because we remove RB, the response of the structure is that it's going to have delta B because we remove RB. Are you with me so far?
Yes.
Thank you. So from previous calculation, again, the calculation of delta B. The formula is for 1L, but this time we have 2L. So delta B will be W 2L to the power of 4 over 384 EI, right? I believe that comes down 2 to the power of 4 is 16, right? So 384 divided by 16, that's 24. So we have WL to the power of 4 over 24 EI. Okay. So step number 4, we'll come back to the business of the calculation of the displacement or deflection caused by the reaction itself. Okay, so this is it. The same beam, the same primary structure, but this time we apply the unit force. And you guys must understand that we have to apply the force where you remove the reaction. Okay, you can't apply anywhere else. And this is basically the same as before because we have done it before. The big M and bad thing is that the moment diagram of this beam is like this, right? So we have to split our moment equation into 2, but they are similar. So we can just write only 1/2 of this and then multiply our integral by 2. Okay. So my big M, if this is 1, this is 0.5, right? So my big M is 0.5x. My small m is also 0.5x. If you want to write star, just up to you, okay? But the range here is from 0 to L, right? Remember that our beam length now is 2L, okay? And here is 0 to L as well. So I can calculate the delta BB. It's going to be integral from 0 to L, 0.5x, then 0.5x dx over EI. But remember, this is only 1/2 of your beam. We can do this because the beam is symmetric and multiply the integral by 2. Okay. So 1/2 and 1/2. So this is going to be equal to x cubed over 6 EI, am I right? Because this is 1/2. Let me be neat. Okay, it's a half. It's a half. That is gone. Okay, and we have x cubed over 3 multiplied by 2. That's 6 EI from 0 to L. Okay, and this means equal to L cubed over 6 EI. Okay. I forgot this, right? 5 here. Okay. So in the end, now we complete the step number 4. We have the displacement due to this. And we can now go to step number 5, which is compatibility. Now we have 5 WL to the power 4 over 24 EI plus L cubed over 6 EI, but this has to be multiplied by RB. It's equal to 0. Remember that this is due to unit load. So due to RB, you have to multiply this by RB. Again, solving this, EI is gone. So your RB is minus 5 WL over 4. Okay, see, it's not a simple beam anymore. Okay, so yep, I think it's time for the break. So try not to keep the video to be too long. Let me stop the record first.